Hi, everyone. This is a talk about dynamic algorithms for graph coloring, and it's a joint work with Christoph Grunau, who unfortunately was not available to give the talk. So I'll try to do something instead. Let me start with a quick reminder about the definition of arboricity. It's a measure of the density of the subgraphs in the densest region. Technically, if you look at any set S of the vertices, we take the number of edges, right, divided by the number of vertices minus 1, round it down, and the maximum of these. By a classic result of Nash-Williams, this is equivalent to another definition, which is the minimum number of forests to which we can decompose the graph. And it's well known that this definition up to a constant factor is equivalent to many other classic definitions, degeneracy, core number, widths, etc. So what about coloring as a function of arboricity? It's a very simple observation that we can see that any graph that has arboricity alpha can be colored with 2 alpha colors. And the reason is simple. We can do the following. We can iteratively remove vertices from the graph, right? That have maximum degree or that have degree at most 2 times alpha minus 1. Okay, so let's remove those vertices whenever we find one. And it's easy to say that there is always such a vertex. The reason is simple. In any graph of arboricity at most alpha, for any set of vertices that remain, the average degree is strictly below 2 alpha, right? Therefore, there's always a vertex that has degree at most 2 times alpha minus 1. Okay, so let's just remove these vertices one by one, and in some sense, let's orient the edges to the vertices that remain. This orientation is something that we will use later on, okay? Orientations of this nature. Okay, now, once we have this kind of a picture, we can start the coloring from the end of the kind of removals and go backward. Every time that we come to a given vertex, right, the previous neighbors, kind of the odd neighbors, have been colored, but they're only at most 2 times alpha minus 1 of those. So we can find the color for this vertex in a palette of 2 times alpha that's not taken by any of the already colored neighbors. Then we color that neighbor, that node, and we go further and further, right? So there's always a way of coloring the entire graph, just in a greedy way, with this proper ordering, and this bound is sharp. This talk is about dynamic algorithms that can compute such a coloring. By dynamic, I mean that the graph is going to go through edge insertions and deletions, and we would like to maintain a coloring of the graph with small update time. For each of these edge insertions and deletions, we would like to have a small update time. There's a subtlety in how do we define this maintaining, right? How do we give access to the colors, right? Perhaps the most natural definition would be that we keep the entire output of all the colors of the vertices in the graph, right? And every time that an update arrives, we just adjust all the colors if necessary, right? Turns out that this is too strict, and there's a result by Barbara et al. That says, if you want the coloring as a function of arboricity, any function, okay, such an explicit dynamic algorithm for coloring would require poly of n update time. So it's somewhat of an impossibility in some sense, right? Good. So, but there's a natural workaround. We don't necessarily need to keep the entire set of outputs explicitly. We can have these implicitly in the sense of maintaining a data structure, okay, that we update quickly with each of these edge updates. And the data structure gives us fast access to each node's color. Whenever there's a query coming in that says, what's the color of a given node V, we can answer that query quickly using our data structure and kind of basically provide access to the colors, right? So the rest of the talk will be focusing on implicit dynamic colorings. So what's known about this problem? The most relevant result for us is work from last talk by Christensen, Nowitzki, and Rothenberg, where they give essentially two main results. One is a randomized algorithm that has polylog n worst case update time and query time, and it gets the number of colors to be, arboricity times log of arboricity, asymptotically. And then a much more technical result, which gets the number of colors to be alpha times triple log n. Okay? But the time complexity, and in fact, more importantly, the query complexity is only amortized. Okay? It's easy to contrast our result with these. We get a randomized algorithm which has order of alpha colors, so asymptotically the optimal number of colors in polylog n, worst case, update, and query times. Okay. Now let me say a little bit more about this prior work, the state of the art in some sense. There are really two ingredients to this coloring problem as a function of arboricity. One is maintaining an orientation of the edges, okay, such that it has a small maximum out degree while the edge updates happen, right? So that's the first ingredient. And the second is using this orientation to compute the coloring. Right? This first ingredient is fairly well understood. For instance, by a result from last SODA by Christensen et al., a different paper by Christensen et al., we know that there is a dynamic algorithm that maintains an orientation with order of alpha out degree in polylog n worst case update time. So this is an aspect that is fairly well understood. The second aspect, perhaps not so much, at least prior to our work, and that's where our focus will be. Okay. Now, having said that, especially with that dynamic algorithm for orientation, what colorings were known? There is a work from 2020 by Hensinger, Neumann, and Wies, where they get a coloring with 2 to the order of alpha colors, where the query time is roughly alpha times log star, okay, and the update time is polylog n, of course. And then the paper by Christensen et al., where besides the randomized algorithms that I mentioned, they also have a simple observation that kind of a distributed algorithm essentially implies order of alpha squared deterministic coloring with polylog n update time, but the query time is poly of alpha times log n, right? But kind of the more technical core of the paper is these two other results, and kind of those are the ones that I already mentioned, right? So going back, this is the main statement of our result. And actually, as a step to this result, perhaps as a simple warm-up to it, we get an extremely simple algorithm that gets order of alpha colors with polylog n update time and polylog n amortized query time. So in some sense, this already is an improvement on that last kind of on the technical ingredient in the Christensen et al. Paper. And I want to actually kind of go through this one slowly. Hopefully everyone understands this algorithm just during this talk. Okay, so let me provide a sketch of these. Quick recap on the setup of the problem. So in general, when we talk about randomized algorithms in this setting, we can assume that arboricity is at most order of log n. The reason is simple. We can just randomly partition the nodes into about alpha over log n parts. And one can see with a one-liner calculation that with high probability, each of these parts will have arboricity at most order of log n. So we can solve each of these parts independently. We can color them independently. We can orient them independently. We don't even need to worry about the edges going to the other parts, right? So we can focus on arboricity being at most order of log n when talking about randomized algorithms. The task for us, given that there is already a good solution for dynamic orientation, is that, there's this subroutine that gives access to an orientation with maximum out degree, which I'm going to denote D. And D is going to be, order of alpha. And alpha we know is not going to be too large, at most order of log n. And we want to use this dynamic orientation to get coloring in polylog n query time. Okay, so generally we will receive, after each edge update and after the orientation has changed accordingly, right? We get perhaps a collection of queries. It says, what's the color of this vertex? What's the color of that vertex, etc. And we would like to answer these queries in polylog n time. And the first thing that we will see is how to answer these in polylog n amortized time. Okay. So let's look at this simple algorithm, right? The amortized algorithm. So in the course of this algorithm, we'll have, we'll keep two sets. One is set T, which is all the vertices that we have colored since the last edge update happened, okay? So this is a kind of a more permanent set. And then there is a set S, which is, at the very beginning of each query to a color, the set S is empty. Then we put a number of vertices into the set S. We color those vertices, okay? And then we add them to T, okay? And then we go to the next query starting from empty set S and kind of eventually coloring all the vertices of S and then putting them into T, right? So in some sense, whenever we receive a query, we might, if that vertex is not already colored, we might color also a collection of some other vertices to answer this one query. And the reason for coloring a few more vertices is to be able to maintain this particular invariant. What's the invariant? It says that I would like to have that for each vertex U, okay, that has not been already colored, if I look at its in neighbors, which, the number of in neighbors can be much larger than D or order of D, right? I would like to maintain that at most 60 of them have been colored. If a vertex ends up violating this condition, I'll put that vertex in set S and I'll color that vertex as well, right, during this query to ensure that I'm not in violation of this invariant. So let's first see why we would like to have this invariant. The reason is fairly intuitive. If we have this invariant, we can maintain good colorings in the sense that you give me some set S of vertices that have not been colored, right? And you ask me color these guys, okay? Respecting all the previously colored, all the previously computed colors, we can do that with, let's say, 9 times D colors. And the reason for that is as follows. Let me look at the subgraph that these vertices S induce, okay? Let's ignore the orientation of the edges inside that. Let's compute a new orientation inside that graph, right? Inside this subgraph G of S, where we get a maximum out degree to be at most 2 times alpha minus 1. Okay, so similar to the orientation that we discussed at kind of very beginning of the talk, right? So now we have this orientation. I claim that now we can compute the coloring for all the vertices of S, respecting even the colors outside. Well, we're going to color these again in reverse order of that orientation, right? Whenever I arrive to the turn of a particular node, right, we have at most 2 times alpha minus 1 out neighbors in this subgraph that have been colored. At most D out neighbors on the outside that have already been colored, right? Anyhow, the total number of out neighbors on the outside is at most D, right? And because of the invariant, at most 6 times D in neighbors on the outside of this induced subgraph that have been colored. Therefore, the total number of neighbors that are colored, which we need to avoid their colors, is small. It's a little bit less than 9 times D, and we can find the color for this one vertex and go to the next vertex and so on and so forth, right? So we can compute any set S of vertices to be colored if we are able to maintain this invariant, okay? That the number of in neighbors that are colored for vertices that are not colored themselves should not be too large. Okay, so going for this invariant, how does the algorithm work? You give me a query for a given vertex Vi. First, I'm going to check whether I have colored this vertex after the last edge update. If yes, I'll just return that color, right? Otherwise, I'll invoke some recursive process on this vertex, which we'll discuss in a minute. And this recursive process will just generate a set S of vertices to be colored, okay? Then I'll compute the coloring of these vertices using what we saw in the previous slide, right? And then I just return the color of this vertex Vi, right? And all of those vertices in S are put in the set T. So in the future, if you ask me about one of those, I can just immediately answer the color of that, right? Now, what is this recursive process? Well, I put, if it's invoked on a vertex W, I put vertex W in the set to be colored, right? But then I also need to worry about the invariant among the out neighbors of this vertex. So I go through the out neighbors of that vertex W. For each out neighbor U, I check, if the out neighbor is not one of those that is in the set S or the set already colored, right? Then I might be creating a violation of the invariant. So I check how many of its in neighbors are in the set T or in the set S. If that number is more than 6 times d, there's a danger of violating the invariant here. So I'll put also the vertex u into the set S. But actually, instead of doing that directly, I'm going to invoke this recursive call on vertex u. And one has to be a bit careful in implementing this condition. You know, we don't want to every time read all the in neighbors of u because there might be too many, but we can keep track of that with a simple, you know, just remembering how many out neighbors have been added to S union T. Okay, so now that's basically the entirety of the randomized algorithm, the amortized randomized algorithm. Extremely simple, right? Let's see why this is good. So I claim that this algorithm has amortized time complexity order of d. D is the out degree that we have, right? And the reason is simple. You know, during this algorithm, really what we do is for each node that we put in S, we're going to check its out neighbors, right? So the total complexity is something like order of S, cardinality of S times d. So the only thing that remains is to kind of bound how large S would be in an amortized sense, right? And for that, let me use a potential function. I'll just take the number of edges that go from the set S union T to vertices that are outside the set, okay? When you query a given vertex and I add that vertex to set S, so that's an increase of +1 to set S, and it's an increase of +d at most to the potential, right? I mean, those edges going out might now be added to the potential. And then whenever I add another vertex to set S, which is by the means of recursive process, right? I might increase the potential by +d among the out neighbors of it, right? But as a result of kind of adding this vertex to S union T, right, or in particular S, I actually decrease the potential by -6d because the incoming edges are now out of the potential, right? So the net effect is -5d, right? So that means in total, the cardinality of S is upper bounded by the number of queries after the last edge update, right, times some constant, right? So that's why the amortized complexity is order of d, right? So that's the end of the description of the the amortized result that we have: order of alpha colors, polylog n query time, and polylog n update time. The query time is amortized, right? Let me say also a few words about how we turn this algorithm into one that has a worst case query time, right? The update time is always worst case, but how do we get also the query time to be worst case polylog n, okay? And here I'll just mention some key ideas, but we won't really go into the analysis, okay? So, you know, what's the main reason that the previous algorithm is only amortized and not worst case? Well, this condition, right, might end up creating a large set S in the course of one query, right? Maybe after a few queries that we have done, for a lot of vertices, they are right at the edge of this threshold, right? And then you make one more query, and then I end up going and checking each of them, putting them in the set S, right? So I might end up generating a large set S. We would like to avoid that. We would like to have that, you know, in the course of every query, the set S that I generate should be small, right? And the algorithm will try to do this with a very small change. So in fact, the algorithm itself is very close to what we had before. The analysis is the more complicated part. The algorithm will try to make this decision in a much smoother way, in a probabilistic sense, right? And one can play with it and see that, you know, kind of a uniform probability of making this decision of invoking the recursion or not doesn't really work, but we can change that a little bit and make something that works. So in particular, every time that I come to this question, right, we'll take a look at that vertex U, right? And it's in neighbors that have already been colored, right? And let's say there are k of those neighbors that have already been colored. In that case, I'll invoke the recursion with probability 1/6d plus 1 minus k, right? And otherwise, I don't invoke the recursion. So, you know, if you think about it, you know, for a given vertex, right, the very first time that I come to it, I invoke the recursion with a very small probability, with a probability roughly 1/6d, right? Next time, 1/6d minus 1, next time is 1/6d minus 2, and so on. And when the number of edges gets very high, gets close to 60, the next time I'm really going to invoke it with a high probability in the end with probability 1, right? So never it's going to go beyond 60, right? But it's a smooth way of going through these probabilities, okay? So as a matter of fact, this is the entirety of the algorithm. It's extremely short and simple. The analysis is a bit complicated, okay? I'll try to give you a hint of the analysis, but I'm really lying about the dependencies, which are the technical core of the result. So let's look into the probabilistic analysis. Let me think about one query that comes in, right? And in particular about one vertex U, right? And I'm wondering what's the probability of triggering a recursion on this vertex, okay? Overall, at the time that it has had, let's say, I of its edges, or what's the probability that ever I trigger a recursion for this vertex, right, with I edges from colored vertices or from vertices that are in S union T, okay? This probability is from the beginning of the algorithm, not the probability at that stage that we have arrived at I of such edges, but from the beginning, okay? So, for that to happen, it must have been the case that the first time that there was such an edge, I did not trigger a recursion, right? So that's 1 minus 1 over 60 probability. Next time I did not trigger, etc., etc. And then eventually, when there were exactly I of such edges, I actually did trigger a recursion, right? And that probability cleanly multiplies to 1 over 60, right? That's a part of the reason that we designed the probability to be like this, okay? Now, if you think about it intuitively, and we are really ignoring important dependencies in this lie of a proof, okay? If you think about each recursion happening only with probability roughly 1 over d or much smaller, let's say by a constant factor, such a thing will not generate a large structure. The reason is that, if I have for each node d out neighbors, and each of them is generating a recursion with probability 1 over 60, the expected number is much smaller than 1, right? And you can do something like a Galton-Watson kind of analysis to argue this, right? More technically or more formally, we can think about every possible way of embedding a tree into this graph, right? There are something like 4 to the z many such trees of size z, right? There are at most d to the z choices of embedding each of these vertices as a neighbor of the previous choice, right? But then the probability of each of these actually triggering a recursion is something like 1 over 60 to the power of z, right? And if I set z to be something like 10 log n or so, this is going to be less than 1 over poly of log n, poly of n. Okay. Good. So with high probability, we wouldn't generate a structure larger than order of log n, and therefore the worst case bound would be small. I'm really, really lying about the proof in the sense that I'm ignoring very important dependencies. That's a technical core of the proof of the analysis, right? But for that, I'll just defer to the paper itself. Please see the paper in how we actually give a formal proof of this and deal with the dependencies. So let me summarize. This paper gives randomized dynamic algorithm for order of alpha coloring, alpha being the arboricity. It has polylog n, worst case, update, and query times. A couple of questions that are interesting and remain open. The constant that we have is somewhat large in front of order of alpha. It would be interesting to see an algorithm that, let's say, gets close to 2 times alpha. Right? And a different thing, it would be nice to see a deterministic algorithm that gets such a result, which has update and query times polylog n in the worst case, or let's say order of alpha times polylog n, but importantly in the worst case. In the amortized case, what we just discussed gives that, but it would be very nice to get worst case one. Thanks a lot for your attention. I'll stop here.